Hello, so we're going to go ahead and pick up where we left off on the last one. We were talking about average velocity. Okay, and so here's a graph of position versus the time of some object. And so we can see it kind of traveling and it goes somewhere. And at this point right here, you can see that it's actually turning around. Okay, so what we're going to do here, if we wanted to find the average velocity, remember, we could find the velocity. Oops. Between 2 points, and so maybe we'll say the points, so that slope rather between 2 points, so maybe between here and here. Okay, or we could find the slope there. Okay, the slope of that line. Okay, but there's other ways to talk about velocity besides this too, right? So let's think about when we're in a car. When you're driving in a car, you can look at the speedometer and it tells you a velocity, or rather it tells you a speed. But the speed that it's telling you isn't the average speed, it's telling you the speed at that instant, okay? And when we find average velocity, like in this circumstance here, this is average velocity, that's not telling us how fast it's traveling at a moment, that's telling us how fast it's traveling over this period of time. Okay, and so sometimes we're going to want to be able to say, well, at this exact instant it had this speed, in which case we need the instantaneous velocity. And so the way we could find it, say that instantaneous velocity at 2 seconds, is we could take this approach with average velocity and we can just continue to decrease the distance away we're using, so like the separation of these time values, we can continue to decrease those until we get to the point where we're very, very, very close, so that the slope of the line is actually tangent to the curve. Okay, so like in this circumstance right here, and the slope of this tangent line would represent the instantaneous velocity, the speed at that instant. Okay, it'd be a tangent line just touching at that one little point. Okay, and so the slope of the tangent line would represent the instantaneous velocity. Alright, so we'll take a look at this graph right here, and we're going to just kind of analyze some of the instantaneous velocities. We're not going to really quantify them yet, just we're going to talk about them. Okay, and so we're going to label some of these positions, or we'll look at the times. Okay, so the first question I have for you is, when is the object traveling, or whatever this object that's moving here, when is it traveling in the positive direction? Would you say, if I gave you two options, when does it have a positive instantaneous velocity? And the options are 2 seconds, or actually I'll give you 4 options. We'll say 2 seconds, 3 seconds, 6 seconds, or 7 seconds. Okay, so when is velocity positive? Okay, and I'm gonna tell you there could be more than one right answer here. Okay, so the answer to this question is going to be actually 2 seconds, because we have a positive velocity right here, and 7 seconds because we have a positive slope right there, and 7 seconds because we have a positive slope right there. You'll notice that at both 3 seconds and 6 seconds, that if you were to draw a tangent line, you'll have a negative slope. Okay. At what times does it have a velocity of 0? We would say that it would have a 0 velocity at about 2.5 seconds and 6.5 seconds. And about at looks like probably at 4.5 seconds too, because it looks like it kind of temporarily comes maybe to a stop right there. It's hard to tell. Okay, and so instantaneous velocity, just the slope at any point. Okay, and so we've done a little work with that. And so it's So what we're going to talk about right now, though, is how we can actually calculate the instantaneous velocity if we don't have an equation for the tangent line. Okay, so here we have a graph that represents the position of an object, okay, and I chose this graph because I actually have a function for it too. So the function for the position of this object could be written as, we're going to say 2x, or we'll say 2t squared minus 4t plus 2, okay? And so this is the function for the position of this object, okay? And what we're going to do is, I want to find out how fast it's traveling at 4 seconds, okay? And so we know from before that we can kind of approximate that by finding, say, average velocity maybe between 6 seconds and 2 seconds. Let's see that, because it looks like that might be pretty close, okay? And so we're going to try that first. So we'll say, okay, average velocity is going to be the displacement divided by the time, okay? We need to find the displacement at 2 seconds and the displacement at 6 seconds so that we can subtract them to find the average velocity. So if we substitute in those values for 6, we're going to get, for 6 we're going to get about 50 meters. So at 6 seconds it's at a position of 50 meters, whereas at 2 seconds it was at a position of about 2 meters. Okay? So we substitute into this formula, the change in position is going to be the second position minus the first, divided by the change in time. So we went from 2 seconds to 6 seconds. That's a change of 4. So it's going to be 48 meters over 4 seconds, which is going to give us 12 meters per second as our average velocity. Okay, and so that's an approximation of the velocity at that point. But what if we actually want to find the velocity at that point at 4 seconds? We would need the slope of that tangent line. So what we could do is we could kind of shrink down this approximation until we got those points be really, really close together. And this is actually the definition of something we're going to be learning about in calculus. And so before I go ahead and continue, I just want you to stop and I want to give you a quick warning. What we're going to talk about right now is something that you have not covered in your calculus class yet, and you're going to learn it the correct way in your calculus class. You're going to take the time to understand the concept behind it. Right now I'm just going to jump straight into the shortcut, and the reason why is because we don't have time to teach the whole background of it in a physics class. So the reason I say this is when it does come up in your class, you want to make sure you take the time to do it correctly so you can understand better why you're doing it, okay? But basically, if we find, let's say that we want to find it at 4, so we're going to say x of 4, and when we find slope, we're finding change in position, so that we'll say the second position is something that's just a tiny bit, just an infinitely tiny bit of time further down, so we'll subtract those. This is x of 4 plus delta t, so some change, infinitely tiny change in time, minus x of 4 over 4 plus delta t minus 4, because this one occurs at 4 seconds, this one occurs at 4 plus however many seconds that have passed. Okay? And using this approach, if we find the limit as delta t, I'm not sure if you're familiar with limits yet, I think you are, but if you find the limit as delta t approaches 0, so if we work this out and make delta t as close to 0 as possible, then we should end up with the slope of this tangent line. Okay, and that's in the background, and what it comes down to with a polynomial like that is that we can actually turn this into a function for the velocity at any instant. Okay, so we can get actual velocity function. And so in order to do so, this process here, we can develop a general rule for when we have a polynomial function to create this other function. Okay, and it goes like this. You're going to take, you have some constant, you have some term, and you have some exponent. Okay? And when we find the derivative, what we do, we call it finding the derivative, and what we do is we multiply this value to that one right there. So cx, and then we subtract 1 from this one. This becomes x minus 1. So if this is a function, this function right here would represent the slope of that function. Okay, so to follow that process here, we take the exponent multiplied by the coefficient. 2 times 2 is 4. And then we subtract 1 from the exponent. 2 minus 1 is 1. Okay. Next term, we're going to do the same thing. This is t to the first power. Okay. So 1 times negative 4 is negative 4. Okay. T to the first, 1 minus 0 is 0. Well, t to the 0 power is equal to 1. So the t goes away. And then finally, in this instance right here, we have 2 times, there is no t here, we could see. It's as if there's a t to the 0 power next to it. Well, 0 times 2 is 0, so that term disappears. And so now we have a function for the velocity. Okay, and so if we wanted the velocity at 4 seconds, we could substitute in 4 times 4 minus 4, so 16 minus 4 gives us 12 meters per second. Okay, and in this instance, we actually have the same value for average and instantaneous velocity based on that region we chose for the average velocity. So let's go ahead and practice this rule again. We'll get a little more complex one. So let's say we have t cubed minus 4t squared plus 6. Yeah, we'll just go like that. Alright, so what I want for you to do is go ahead and write a function for the velocity of this object. Okay, think about that rule I just gave you. And I want you to try to apply it right now. It's okay if you don't get it 100%. That's not the goal right now. The goal is just to give it a try and see if you can do it. Okay, so after you tried it, let's go ahead and work it through together. We take the exponent multiplied by the coefficient. 3 times 1 is 3. And then we subtract 1 from the exponent, so 3 minus 1 is 2. Take the exponent multiplied by the coefficient, give us negative 8. Subtract 1 from the exponent. Okay, to the first. Finally, 6 times t to the 0. 0 times 6 is 0. So that term goes away. And so here we get that function right here. Okay? And we'll go ahead and wrap it up with that. And we'll get a little bit more practice in the next one on the difference between instantaneous and average velocity.